This is topic 24, electrochemistry of A levels chemistry. Now, before going on with the topic, we need to have some concepts revised from the chapter redox reactions from AS level chemistry. Now, if you remember from redox reactions, we learned about oxidation numbers, we learned the rules of assigning oxidation numbers, we learned about oxidizing and reducing agents and what does oxidation and reduction means and the ways through which oxidation and reduction can occur. Now, what I want you to do is to pause the video and work out the species in each of these three reactions that gained electrons, the species that lost electrons, the oxidizing agent, and the reducing agent. Go on, pause the video. Now, if you pause the video, you must have worked out that copper, bromine, and lead were reduced, or they gained electrons, or they were oxidizing agents. Meanwhile, iron, copper, and sulfur lost electrons, were oxidized, and acted as reducing agents. Remember, something that gets reduced oxidizes others. So it is an oxidizing agent, and something which gets oxidized reduces others. So it is an reducing agent. Now I know the first two reactions must have been easy to work out, okay, and assign oxidation states. But some of you may have been confused in the third reaction, and this is a mistake I did when I tried to work out the oxidation numbers in the third reaction, which is that I assigned oxygen to be -2 because oxygen is always -2 except for some special cases. So -2 into 4 is 8, -8, and I know the overall oxidation state must be 0. So the oxidation states of lead and sulfur must add up to 8. But that is a very vague answer. How do we know what the values are for each of them? It might be +3, +5, +2, +6, +4, +4. Okay, so that is not how you will figure out the oxidation numbers. You need to consider SO4 as the ion, okay, and we know that sulfate ion has a oxidation state of -2. So lead is +2 here. Okay, so this is +2. We know this is -8, after multiplication and all that. So sulfur is +6. And now we know that sulfur has lost electrons and lead has gained electrons. Okay, now here we have two ionic half reactions, and we need to revise how to make an overall ionic equation from half ionic equations. What we'll do is that we will equalize the number of electrons being used and produced. So we will multiply this equation by 2, and then we will rewrite both equations. Okay, now what I'll do is that I'll combine the reactants together in both reactions and combine the products together in both reactions. I've highlighted them so they are clearly visible to you, and now I can see that the 2 electrons is same on both sides, so I can just cancel it. Okay, and then I'm gonna write the overall ionic equation. 2i minus plus H2O2 plus 2H plus, and it gives I2 plus 2H2O. Now let's move on to electrolysis. Electrolysis, it is the splitting of a substance, lysis, using electricity, electro. Okay, so this explains the name. In the electrolytic cell, the electrodes are rods made of carbon. The anode is the positive electrode and the cathode is the negative electrode, and the power supply is direct current. So basically you supply direct current to any compound you want in its molten or aqueous state, and you split that compound. Okay, the cations go to cathode for reduction and the anions go to anode for oxidation, and you get metal or something, it might be a gas as well, deposited on each electrode. Okay, the product formed from the cation and the product formed from the anion deposited on each electrode. The products of electrolysis depend upon whether the electrolyte is molten or aqueous, and in your O levels you studied this long mechanism of working out which product will form in case the solution, the electrolyte is aqueous. Okay, you had to consider H plus and OH minus ions as well, and you had to learn these reactivity series. But in A levels you don't need to learn any reactivity series. Okay, you will be given something called electrode potential values, and the ion with the most positive electrode potential value will be reduced, and the one with the most negative electrode potential value will be oxidized. What is a galvanic, voltaic, or electrochemical cell? I want you to ignore all the information you're seeing in front of you, okay, and just focus on this. diagram. Okay, this here is a galvanic cell. Okay, we have two electrodes. What happens in a galvanic slash voltaic or an electrochemical cell is that one electrode dissolves and one electrode increases in mass. Okay, so this electrode here, which is the anode, dissolves, and this electrode here increases in mass, and it is the cathode. Oxidation occurs here. Okay, the metal basically just the reaction occurs in such a way that the metal is converted to ions. Okay, and the solution increases and the mass of the electrode decreases. Okay, and electrons flow from this wire to here, and the ions react with these electrons, basically combine with these electrons to form the metal of the cathode. Okay, so the electrodes are basically taking part in the reaction, right? And we are producing electricity, we are producing the flow of electrons, and which metal dissolves depends upon the electrode potential. Then we're going to study that later. Of two half cells. Okay, and unlike electrolytic cells, we produce electric current, and the electrodes take part in the reactions. Okay, previously in electrolytic cells, the electrodes were only there for deposition or for conduction of electricity. Okay, but here the electrodes take part in reactions. The anode here is negative and the cathode is positive, which is opposite from the electrolytic cell, and we do not require an external voltage source since we are producing the electric current, right? Instead, we use a voltmeter to measure the voltage of the current we produce. The half cell with more positive electrode potential gets reduced and the more negative electrode potential gets oxidized. So the same principle as the electrolytic cell. Okay, the half cell with the more positive electrode potential gets reduced and the more negative electrode potential gets oxidized. You need to remember this fact for both an electrochemical cell and electrolytic cell. Okay, now how do we construct half cells? We can build half cells by taking a metal and placing it in a solution containing the ion of the same metal. Okay, so this is a half cell, right? We have copper metal dipped in a solution that contains copper ions. To make a whole electrochemical cell, we connect the half cells with wires and add a voltmeter and a salt bridge, and voila, you have your electrochemical cell. Now here we have a voltmeter to measure the voltage. We have a salt bridge to allow the movement of ions. So there's no charge accumulation. If there's charge accumulation, the electric current won't flow and the process will stop, right? So we need our salt bridge. We need two beakers containing the solution. We need our electrodes and we need wires and voltmeter. And this is how you're going to represent an electrochemical cell in your exam. It is often asked to draw and label a electrochemical cell. Okay, so this is how you're gonna draw and label an electrochemical cell. You're gonna show the flow of electrons with an arrow. You're gonna label the voltmeter, the salt bridge, and no need to label the beakers or anything. Okay, and you need to label the ions in the solution, and you need to label the electrodes, what are they made of, and which is the cathode and which is the anode. Okay, so again, as we studied, the one with the more positive electrode potential value gets reduced and the one with the more negative electrode potential value gets oxidized. So Zn here, zinc here, gets oxidized, which means the electrode kind of dissolves, right, to produce ions, and it gets oxidized and we produce electrons which flow from here to here. And since copper has a more positive electrode potential value, it gets reduced instead, right? It gets reduced instead. Cu2 plus reacts with the electrons that have come to form copper, and we have deposition of copper on this copper electrode. Okay, so more copper forms here and the zinc anode dissolves, right? And until the zinc anode fully dissolves, until the zinc anode fully dissolves, the process keeps on going. Okay, now if you were confused about what is standard electrode potential and what is electrode potential, you need to know about standard hydrogen electrode first. It is used as a reference to measure standard electrode potential. The SHE is basically a hydrogen half cell and has an electrode potential value of 0. We need to have standard conditions like temperature of 298 Kelvin, pressure of 100 kilopascal, and concentration of ions at 1 mole per dm cube. Okay, the voltmeter reading we get after connecting SHE to a half cell is the standard electrode potential for that half cell, right? So whatever value we get here after connecting this half cell with the SHE is the standard electrode potential value for this half cell. You can also calculate standard cell potential. It is the voltage reading of two half cells connected in standard conditions. This formula can be used to calculate standard cell potential. E naught cell is equal to E naught reduced minus E naught oxidized. That's all.